Everyone. Hello, how are you? This is Joshi, and today we are going to discuss about our work on cryptology and how we used geometrical frameworks to build our own crypto system, which is quite efficient in its own sense. We performed under a humble guidance of Professor Manish Gupta, Professor Manoj Raut, and Professor Prosenjit Kundu. Moving on. Okay, so brief about ourselves. Okay, so this is our website, and this is us, a small team of six. And as an individual, I would like to add a note over here that it was a very good time working with each other as an individual, as a team. It was a great opportunity to learn and build leadership qualities. Also, I would like to say the workspace that was created and the fun we had were surely the legitimate and the best part of this project. And I hope that yeah, further in future we again come up with some new work, some new ideas, a fresh start. Okay, so moving on with a positive start. Okay, so I would like to give a brief to our readers, or to be precise, to our viewers. For this project, we would, with all humble consideration, we can proudly claim that each and every part of this project, even the minute details and the content and the flow, the algorithms, the code, each essential part is firmly handcrafted, and we didn't just explain the currently existing, admired, and currently industrially used works like the RSA, ECC, and AS. Rather, we just took inspiration from them and used them as a fuel, and we created our own dimensionally independent work. And we are proud to say that. And during that time, we also learned, we also made some mistake, we also uh, gave a lot of time solving those mistakes, and that was quite fun working with that. Okay, so moving on. Okay, so let's begin. Now, I would like to just say that uh, this digital world, we are surrounded by the sea of ones and zeros. Now, it's not just a luxury, but a necessity for us to have a security in such world, because otherwise, it would be completely random, dismanaged, and disoriented, and that would be a complete mess. We don't want that mess. Okay, and we as humans have now upgraded ourselves to even more stronger computers and systems which could create threat to us. So to satiate those needs, we constantly work towards the field of cryptology. And as also interestingly we mentioned in our PDF, we could just say that encryption is like salt in food. You see, we do not notice its presence, but if it's absence, we'll never, the food is pale. So uh, cryptology is a must, and with time we must update them so that we could satiate our needs and the security. Okay, so moving on now. Okay, so here's the interesting part. Okay, so the main ideology of a project. Well, the idea of this project, to be honest, came to me when I was dressing in front of mirror. Well, uh, also I was just thinking about cryptology at the time, randomly just and dressing, and I just thought that why not use this imaging, this process of creating image as a trapdoor function. Okay, so let me first clarify the term trapdoor to be precise. I mean, trapdoor functions are just the function which are very easy to solve from one side, and uh, from other side, if you want to solve, they are very difficult. For example, let me give an example in our project sense. Let's say I give you that at this point an image will be created. I just give you that information that at this point an image will be created, and now that I ask you that now tell me where the object is, you can't do that, right? Because you don't know where the mirror is, right? You just know an image has formed here. You don't know where the mirror is. But on the other hand, if I tell you that this is the mirror, this is the object, you could always find a particular and a single solution to that, and you can find a single image to that. Okay, so that could be employed as a trapdoor function. And rather to be precise, as I mentioned image, I would like to just redefine that term. We use deviated image. We will discuss about that in further part of our video. And also I'd like to say that we use that geometry of images, the deviation, and created this system. And we call it, the system as the geometric encryption using deviated image. And this is using that part of image to encrypt certain quantities. Okay, so moving on to further, I would like to add that the quantum threat. Now, what's that quantum threat? Okay, so quantum computers that we are building are becoming robust day by day. Now, the quantum computers are not the trends of future; they're happening right now. Their growth is exponential, and by day to day, they're creating a constant hazard to currently admired solutions like the RSA. Now, how they are creating threat? Well, you see that there is a framework on which every encryption system lies. For example, the RSA. It has a very big prime number, and the whole cryptology in that is that it's difficult to factorize them. But trust me, quantum computers can do that in no time. So that therefore they could ransack the RSA structure or any other vulnerable crypto system currently existing, even the AES. So the many internationally recognized institutes and agencies like CIA and NSS have adopted policies that in which they are trying to build, even NIST say they are trying to list down and get idea of and try to build such a system or build such a crypto system that could withstand this quantum attacks from these robust systems. Okay. Okay, so moving on. Here are on your screen some cryptographic schemes. And now we have classified them. On the leftmost hand side, you have the RS encryption and the Diffie-Hellman key exchange, and also the famous ECC from Bitcoin, which are not particularly quantum safe and they are quantum vulnerable. Then there are in the middle the lattice-based cryptography. As a fact, I would like to share with you. The NIST listed currently the latest based cryptographic works from the Crystal Kreiber's work, and they consider them to be quantum safe because they use certain sets of vectors to create a lattice field. And there are saying that pair of good vectors and pair of bad vectors. So they are in a way used to achieve that trapdoor function which I mentioned earlier, right? So, and there are some more like code-based cryptography, the error coding we generally refer to them. Then there is hash-based cryptography. Then there are some cryptography schemes on right as you see, which were believed to be quantum safe, but they are said that they could be defeated by the quantum computers. Okay, so moving on. Now, as I mentioned, there are some popular pre-existing cryptographic schemes like AES and ECC. ECC is prominently used in Bitcoins and other blockchains. Okay. Now, here comes geometrically quantum resistant schemes, as I said. But okay, so let's first say what is geometrical approach or geometrical framework that could be employed to build a trapdoor function. For example, ECC, we use that curve particularly and the relation as a keys, as to generate keys and use them as a trapdoor function. Also in this lattice, there is in the same way. Meanwhile, okay, I just forgot to say that, but that ECC I mentioned is not quantum safe. It's vulnerable to quantum attacks. But here I would like to describe about lattice-based cryptography, which is listed by NIST to be quantum safe. And to be precise to it, it is also believed that it's safer than even the current version of AES, which is the 256-bit key. Also, we just thought that why not we also use the coordinates and the lattices and plot them as message points and work with the geometry of those points and the schemes, try different scheme, and we came up with this scheme of image, converting that points image and then deviating it and that factoring that distance, which I'll just explain in the further videos. First, I mean the further part of the video to be precise. Okay, so giving brief about this, there are a pair of good vectors and a pair, let's say them to be good vectors, which help us to create a lattice very easily, and there are a pair of bad vectors which have very minute deviation from each other, and to reach a point from origin to say other point lying in that lattice using bad vector, it would be quite cumbersome. And but if you know the good vectors, you could just get easily to that point and find what exactly the message was, so that it works on that shortest problem of the shortest vector problem, which is quite famous in this field of cryptology. Okay, so giving brief to that, moving on. Okay, so our solution. Here comes our solution. Now, in our approach, though we have just described in our presentation the uh, two-dimensional version of our solution, we could extrude that in multi-dimensional, and we could also extrude that idea of image deviation in multi-dimensional. Now, how that works? Okay, so how that works, we're gonna try to understand. Now, our approach is asymmetric one. Uh, uh, that is that it will require two keys. The first one is to encrypt it, and the other is to decrypt it. Okay, so there will be two keys, private and the public key, right? Now, we define image not to be a regular image, like just we see that in mirror, right? Just normal to ourselves and at a distance exactly equal to the distance of object in mirror. Rather, we define our image in this context to be the image formed after multiplying the distance between the object and the mirror with some factor k, and deviating that point with respect to angle theta, so that k times that distance remains constant, right? So that's more mathematical. We'll just get some intuition afterwards, as I just mentioned some graph and the diagram. Okay, so moving on. Okay, so here is the graph of our geometrical encryption using deviated image. Even it's mentioned in our website, you could see that in the introduction. Okay, so here is the graph. Okay, so what's in particularly in that graph is that, as I just mentioned you, that here is the x0 y0 point, so the sender must convert his message to a message point, just like as we do in lattice based cryptography, that is the Crystal Kyber's work. And then there is a line, ax plus by plus c equals to 0. Now this is 2D version of it, so there is a 2D line. Now there could, if 3D, that would be a plane. If 4D, there would be some other quantity, physical quantity, some other physical meaning. Now what I'm doing is, as I mentioned, I would define a k. I would define an image such that it's k times the encrypting factor, which would be a private key to me, and at angle encrypting angle theta, which would be again private to me, with respect to line ax plus by equals to c, which would be again private to me. Okay, so now here are some fundamental values to this abbreviations, upper mentioned abbreviations. For example, the D, the L cap, the P cap, these are just derived from using basic vectors. Okay, so moving on. Now in this method, as I mentioned, this is how we work through it, that how we use the vectors. For example, we could say that initial point to be have a position vector of r0, and the final image, let it be having a final position vector to be r1 vector, and let the p cap be the direction that is directed from foot of perpendicular of the image of the object point, from vector starting from the foot of perpendicular of the image point to the image point, right? And the unit vector in that direction, that would be a p cap. And then we have the L cap, which would be along the line. Now, and then we applied this geometry and said that r1 vector is nothing but r0 vectors plus k plus 1d times p vectors, and by using geometry it's plus kd times tan theta times l cap, right? Okay, so then there is 4 hard maths followed by it, and we just use that as I just mentioned. Now we take this and then we get this d. Now using this we get this encrypting function. Now what is this encrypting function? That would require two values as a plugin, x0 and y0, and we will already just take values of a, b, k and theta, and that would be private to the receiver, and we'll construct this function, and this would be public to all. Okay, this will be public to all in a way that we would just put the values here, so that after putting the values, for example, I say I put theta equals to 3 point something degrees, or say 90 point something degrees, or 80 degrees, something randomly, or some put k equals to 86, or some random numbers in some highly hard decimals. It could be anything, it doesn't matter. In code we are going to see that it particularly doesn't matter. Now then if you, now this s0 is nothing but that, s0 is nothing but you put that point in the line, right? S0 is nothing but ax0 plus by0 plus c, and if you see s1, that's just corresponding to it, that is ax1 plus by1 plus c equals to 0. Okay, so that's to mention. And after, if we put values to it, one cannot factorize those values and come back to this equation and find the values of abc. Even in 2D it's hard, and now when we extrude our idea to multi-dimensional, say 50 dimension, 100 dimension, I don't and I would like to say that it's not just like as claimed in lattice-based cryptography, that extruding that idea of lattices in say 100 dimension, it becomes an unbreakable challenge to quantum computer. So if we extrude, apply same logic here, and we extrude that our point may be in many directions, let's say 100 dimension, and one of them is the message dimension, then I don't think that it could be factored back to this equation and one could get values to it. Okay, so we'll jumble this function up after putting the value, and then we have this decrypting function, which would be again private to me. Now let's see how encryption and decryption are working in real time, right? So that we could have more clear understanding. I mean, in this page it is explained in text, but let's try to, I'll try to explain that verbally. Hope that the explanation is good. Please bear with me. Okay, so starting, first thing first, if you have a message, say b, letter b, so letter b must have some value from ranging, let's say 0 to 25, so that be 1, let's say 1. So okay, a has 0, so b has 1, let's say 1. So what I'll do is, first of all, the receiver will have the pair of a, b, c, k and theta, which would be private to it. Okay, no one would know the value of it. Now after using those values, he will just design this encrypting function to all. Now when the sender want to send a message to receiver, he will just go and plug in, choose any dimension, it could be x dimension or y dimension, plug in that value, say b equals to 1, so he'll plug in 1 in, say, let us take x0, so he'll plug value 1 in x0. So after plugging in that value, now he'll randomly, now this is the crucial part that he'll randomly assign value to y0. It could be any random number, that could be very difficult to guess. And now imagine if we extrude this in multi-dimensional for, let's say, 100 dimension, then there will be exactly one message dimension. It could be any of it out of 100 such dimension, x, y, z, something, then extruding x, y, z, etc, something, that could be any dimension. And the other 99 numbers, other 99 dimension would be random numbers and cannot be guessed. Okay, so that's the level of hardness we could achieve by using this encrypting scheme. Okay, so first, as you put this value x0, y0 in this encrypting function, you will get an image, as I mentioned, x1, y1. Now given x1, y1, now you'll give me this coordinate x1, y1. Now if there is, assume there is tapping in the line, so there is some intruder who is constantly tapping our conversation. So now what we'll have? He'll have two things in his hand. The first thing he'll have is the encrypting function, right? He'll have the encrypting function, and the second thing that he'll have is the image point. Now, the thing, a funny thing is he cannot do anything with that because he has just the encrypting function, not the decrypting function. He cannot use that image point and the encrypting function to reach the final point. Now, let's say if he puts that image point in encrypting function, then that would be equivalent of saying that it would k times produce image at angle theta, which would be lying somewhere. Say if I just mention it, sorry, bear with me, but if I mention it roughly, I would say k times the distance and at angle theta. So that would be here around somewhere, and that won't be our answer, right? So it cannot reach to the message point, right? So that's the catch. Now, what if I use angle phi? Now I design another function with angle phi and distance 1 by k. So you see here, that would be my decrypting function. Now how that would be a decrypting function, I'll explain it to you, right? Now while encrypting, what we are doing? We are multiplying the distance by k. So now we must multiply the distance by 1 by k, right? Okay, so that's dividing by k. Okay, so if this is d, this is 1 by k times d, which is d, right? So we are reversing back the effect of the encrypting function, and now we'll deviate it by angle phi. Now how do I calculate this phi? Basic geometry. This will be kd tan theta and this would be d, so that would be tan inverse k times tan theta, right? Okay, so now I know the phi and I know the k. Okay, so I'll design, or I'll have pre-designed decrypting function. Now what I'll do, I got that image point from my sender. I'll put them in here and get my final output x0 y0. Now I'll check for which value did that sender put, which in which dimension, it could be x or y, he would have used as a message dimension, and I will get the message from that. Now we'll see that it clearly works and works very efficiently in code. I'll describe that later. Okay, so again I would like to say this thing whole that happened here was nothing but first we do something, like for example a trapdoor mechanism that we design, we declare k theta in this line, we design an encrypting function, and we design another function that decrypts or the nullifies the effect of encrypting function and gives us back the original point. And that's how the system works. Okay, and these are the nodes and these are the scribes we used, and how we actually, what were the mathematical framework that we used is mentioned here, and how we solved this whole thing. Okay, so this was all about it. Now one more thing I would like to draw attention is that x0 and x0 and x1 and y0 and y1 are inter-replaceable to each other in encryption and decrypting function, as you could easily see here, right? Now the only change is that you change k with 1 by k. See here, k is changed with 1 by k and theta is changed with phi, right? Okay, so that's the basic change we mentioned here. Okay, and the logic why we did that is all as I explained why we did that. And now here is the boring text. Okay, okay, sorry for that, but we have written this text, and then here is the working and the inheritance part of it, that how, as I mentioned, it is working, and how we inherited, as I said, that how we inherited the idea of message point from lattice cryptography, and how it is cannot be solved by hit and trial method. Now one more thing I would like to say, like in AES there is a multi-layer of it, right? This there is not one time it's happened, right? This if there is system like say imaging, the AES would have done that in stacks. So for that it would do it once, do it again, like many of times, and then reverse in that same order. So here also we can do it. For example, I say I take this image message point, then I construct its image using some function 1, encrypting function 1, then I plug in that image into encrypting function 2 so that I'll get another image, then I can again use encrypting function 3 and plug that image in that and I get another image. And when I want, I would just use their corresponding decrypting function in that particular order, and I again could trace back to my original message point, right? So that could be multi-layer to it. Also, we could also spread it in multi-dimension so that it becomes unbreakable even by the quantum robust systems, right? So that was all, right? And I think it is quite efficient. We also discussed it with Professor Manoj Raut, and he was quite happy. And we also are thinking that if we get a chance, we would surely work in this field, and would like to even contribute to research culture of our college, right? Okay. So again, that's all that I said is mentioned here. One could read it. Now here is an example. For example, let's say Utsav wants to send a message to Shyam. Then this is how we'll set theta. Don't worry, I'm going to show this further in our code, right? Okay, so these are some references we used. Now I would like to draw our attention to our website. Here it is. Okay, so here is the source code. Okay, so you could copy it from here or run directly. It would open an IDE for you. Now let's just quick run it. I think. Okay. So for example, Bob wants to send a message to Alice. Here is our code. For example, I choose value of theta to be 61.23 something randomly. Then I choose value of k to be 3, value of a to be 2.3, value of b to be 6.56 something something. And okay, I would like if it's random numbers so that we could get some random solutions to it. Now I would like to choose a random number. That would be the y coordinate for me, obviously. Let's say 64.555 something. You could have chosen even a big number, right? For example, 3. This is a big number, right? Okay, so I choose this number, point something something. Okay. Now I'll write my message. Okay. Right. I wrote the message and I pressed enter. Okay, so here it is. The function converted the letter M into its corresponding message point and thus converted that message point into final image point. You see, right? So these are the image points, right? You get this image point, and after that, for example, if I say write any key, right? You have a message from Bob. If I want to view that message, here is the message. So that again these points are used, and we get back the original number, right? So original message is in the. This is how we use our scheme. This is the whole code to it. Here is the decrypting function in the private domain, and here it is in the public domain, right? So that's it from our side, and hope you had a great time. And please bear with me if I had made some mistake. Kindly contact us if there is further discussion that could be more elaborated. We'd like to have arranged some discussion about it. Okay. Okay. That's Dev Joshi signing off. Thank you.